Tēnā koutou katoa. My name is Shane Clark. I'm the General Manager here at Nuralite. For those of you who don't know, Nuralite is synonymous with flat roofing and waterproofing and has been so for the last 50 odd years. So our webinars are set for around 30 minutes. We try and keep them short and sharp. We appreciate your time is very, very precious. I encourage you to participate where you can, otherwise you're going to be looking at me talking at you for 30 minutes and it won't be that exciting. So please use the Q&A function, the chat function, and the polls that will pop up from time to time. I do think that you get from these things what you put in, so it'd be great for you to participate in these events. What we do with our charities, with our webinars, is that we donate to a charity every time we do a webinar. Typically, we allocate a marketing budget when we're doing a presentation to architects, which usually consists of sausage rolls. Obviously, we can't do that at the moment to certain lockdown levels. So what we're doing is we're donating $10 for every participant to a chosen charity. Now, our charity today is Parkinson's New Zealand, which is chosen by our panelists. So thank you very much for everyone participating today. You already made the world a better place. So good on you for simply being here. All right, lucky for you all, I'm not the only one on the panel today. You get to talk to some other people other than myself. I've got producer Jay pushing some buttons behind the camera there. Very useful. We have Peter Mills, our internal technical advisor here at Nuralite. He's our very own Gen Z and our all-around sort of whiz kid. We're also very honoured to have Denise Martin, Principal Analyst at Oculus Architectural Engineering. Denise is an accredited passive house certifier and classed as one of New Zealand's leading experts in building science. So thanks for coming, Denise. It's great to have you here.
Thanks for
having me. So what we want to talk to you about today is basically we've picked three design considerations we think you should consider when specifying a warm roof. I'm going to flip to our first slide there, Jake, with our considerations. We have taken the assumption that most people are familiar with the warm roof concept. So we're just going to throw to our first poll. Jake, you want to chuck that up? We've assumed that everybody's familiar with the warm roof concept. So this is a more of a deeper dive into some of the, I guess, unique finer details of the warm roof. So just give you a second to populate that poll. All right, thanks for that. So the key points we want to cover today are the three considerations we think you should consider when specifying a warm roof. The first one is, when is a warm roof not a warm roof? And that's the piece that we'll have Peter covering. So we'll be talking about the thickness of PIR board, Nuralite's definition of a warm roof, what we actually class as a true warm roof. We're then going to cover the effect of mechanical fixing through a continuous insulation layer. And that's where Denise comes in with her science or magic, if you like, and shows us some calculations as what we are doing with our fixings. And then I'm just going to briefly finish at the end to talk about some additional layers of protection or additional layers of redundancy we can build in when we're designing a warm roof. So those are our intentions, what we want to cover today. So we're just going to go to our first panelist, Peter Mills, to the third slide there. So like I said, Peter is our internal technical advisor here at Nuralite, and he is our all-round whiz kid, and we're very lucky to have him, being able to drive a computer and all the technical things he can do. How long have you been at Nuralite, Pete?
I've been here for 3 years, Shane. Started off not knowing what a flat roof was, and since then kind of soaked up as much information as possible, and fallen down this building science rabbit hole in recent years.
Excellent, mate. Excellent. So what we're looking at here basically is a render, a cross section of an example of a Nuralite warm roof. If you just can quickly run through some of the components there that make up a Nuralite warm roof.
Yep, so the first layer you'll notice on the bottom is the metal tray. That's a substrate and can be changed out for a few others. The key components that we're interested in here is a vapor blocker that's immediately on top of that substrate. a rigid insulation layer that's on top of that. It's got the rating on it, and then we've got thermally broken tube fasteners that go through that insulation. On top of that, we've got a waterproofing layer, but the three most critical components here are that vapor blocker, the insulation, and the thermally broken fasteners.
Excellent. Thanks, Pete. All right. So, like I said, the first point we're going to talk about is when is a warm roof not a warm roof? So, Pete, how do you work that out? What do you have in your arsenal to prove that? If we just flip to the fourth slide.
Yep, so we use a piece of software called Ubacus. It's a hygrothermal calculator provided by our manufacturers. It's quite a well-known software package. It uses something called the Glasser method, taking a two-dimensional cross-section of the building as a static point in time, and it uses that to calculate the hygrothermal performance of the system. I know that's quite a mouthful, but basically it looks at whatever materials you put into it, and it figures out what the performance of that build-up is going to be in terms of insulation, and whether or not it's going to produce interstitial condensation. It is not as sophisticated as the Woofy method, but it still kind of gives a good idea of performance of that build-up. I liken it to a windsock to a weather station, where Ubacus is the windsock and Woofy is actually the weather station. They're both useful, but one of them's more sophisticated than the other.
Excellent, mate. So, what are the things that sort of define what a Nuralite warm roof is? What do we define as a warm roof?
Well, the two most critical components we're looking for are proper vapor control. So typically that would be a vapor blocker, which is what we do with our bottom vapor blocker layer. And then the second thing we're looking for is sufficient insulation to stop the formation of interstitial condensation. It's kind of a bit of a rhyme.
You're a poet and you didn't know it, Pete. Good on you, mate.
Yep.
No, excellent. So what we've seen in this example here, some of the typing is a bit small on the slide. So we're only seeing, I guess, a very slim 40 mils of insulation on top of a profile metal tray.
Yeah, that's correct. Basically, all that we're seeing here is a metal tray substrate, some rigid insulation, and then a membrane layer. There's not necessarily a dedicated vapor control layer, and it's actually quite a small amount of insulation. What you might be able to see is that the R value for this build-up is only about 1.68, which is well below what we would call a true warm roof in Nuralite's view.
Excellent. So I think the graphic there kind of gives it away. You've got little water droplets in there, which to our way of thinking is a no-no.
Yeah, in terms of this software, that's a big red flag. That means that there's strong potential for there to be interstitial condensation formated, and that can either cause a problem for the membrane that you've got at the top, or it can go down into the structure and cause problems there.
Nice. So your next slide, Pete, you've done the same sort of calculation, but you've run what we call our warm system through it.
Yep. So this one, we've got our standard layers. So we've got our vapor blocker sitting on top of the substrate. You might just be able to see it. It's the little dotted line just underneath that insulation core. Then we've got at least 70 mils of our PIR board, which gives an R value of 3.15. And then on top of that, we've got our membrane layer. So the three of those together are able to stop the formation of interstitial condensation. This was in terms of Auckland's climate. We need a bit more when we go further south, so like Queenstown, Christchurch areas. But for Auckland and anywhere north of the Bombays, that build-up is sufficient.
Nice. So sorry, Pete, just to recap, this is the Auckland climate, is it right? Roughly?
Yeah, that's right. That's the values that we've put into the calculator here. We're able to use the software and basically put the temperature and humidity ranges of other areas of New Zealand, but we've used Auckland this time around.
Excellent. No, that looks really good. So obviously, what we've seen in this graphic here, what we saw in the last one, is we've eliminated that moisture, which is something that we're trying to eliminate.
Yeah, and so pretty much in simple terms, the previous slide had water droplets, where this one does not. A pretty easy graphic giveaway.
Excellent, mate. Thanks. We've got a few questions and comments coming in, which is fantastic. We'll have about 7 to 8 minutes towards the end. Hopefully, we'll cover those all off. If we don't get a chance to cover them all off, you'll actually get sent this recording for posterity, along with a copy of all the slides and the Q&A documents. So if we don't get through all your questions, we'll definitely get to them. So if we want to flick to the next point, Jade, that we want to talk about today. So the second point we want to talk about, and we're lucky to have Denise here to help us with this one. So with the Nuralite warm roof system, we typically use a thermally broken fixing, as you can see in the center of your slide there, as opposed to a standard screw fixing, which is a conductive steel screw. This is a tiny wee screw, which I'm not sure how much consideration people give it, but it is quite interesting to see what the effect of it is. So welcome, Denise. Thanks for coming today. Firstly, who's Oculus and what do you guys do?
Who are we? Thanks for the introduction, by the way. I hope I'm not considered the one of the leading ones of the building science community here. Otherwise, we're in trouble. In terms of Oculus, we are predominantly facade engineers, and I personally just have followed the passive house pathway through becoming a designer a number of years ago and recently becoming a certifier, and sort of specialized along those lines with hydrothermal performance over the years, as it all feeds into passive house to some degree. I also do thermal bridge calculations and so on.
Nice, excellent. So that's obviously why we got you here today to talk about thermal bridging, and when we talk about mechanical fastening. So if we just flick to your first slide, you'd be able to run us through what you're showing us here.
Yeah. So the standard that we would apply in passive house is based on the European standard 6946, which is basically the equivalent to our New Zealand NZS 4214, to calculate the total R value of material in construction systems. So there's an appendix in that standard that helps us approximate the influence of a metal fastener through an insulation system, because in Europe we do have a lot of external insulation systems and need to make some approximations on how the fasteners impact on the performance there. Ideally, you would do a three-dimensional finite element analysis or thermal bridge calculation in order to determine the exact thermal bridging value, plus also the surface temperature that may be affected. But for this exercise, we've used the approximate calculation method as per the standard. So you can see that I've showed you the formula here where the U value supplement can be calculated. So if you're familiar with the R value calculation table from PHPP, which is in the bottom left of the slide, where you enter all the layers, very similar to how you calculate it in New Zealand with the different material layers, the thermal conductivity and the thickness of each layer. And with this value that we calculate as a supplement, we enter that in the little table down the bottom that are marked out red.
Yeah, right. Okay, and I think on the next slide you've got some actual calculations you've done for us.
Yeah, so as an example, here we've used the 80 mil deep plastic fastener with an actual penetration depth of 20 mil for the screw fixing, the actual metal fastener, and given you the example calculation of what that would look like if we were to calculate the R value of the construction system. So I've layered the Nuralite roof in the table here with the roof membrane, the PIR insulation, then the vapor barrier and the metal tray.
Nice.
And the total R value in this linear approach would be 4.115. And then given the input data to complete this formula above.
Yep.
And if we go to the next slide, we can actually see what the resulting R value is.
Yeah, so I mean, when we look at one screw by itself, it's not such a big deal, but we do know that from our specifications, it's basically a standard specification. We need 6 fasteners per square meter, because I mean, this is what's holding the warm roof down to the structure. So
Yes.
this example here, we've got 6 fasteners per square meter, which has a cumulative effect.
Yeah, and as you can see, if we're using the 6 fasteners per square meter, we're ending up with a supplement value of 0.06 watts per square meter Kelvin, which then leads to a correct R value of 3.2, which is almost an entire R lower than without the fasteners. And this is using the thermally broken fixing solution. So in comparison, we looked at what would it be if we use the standard fixing, where the screw penetrates the insulation from inside to outside, and the supplement is 0.31, which is about 5 times higher than using a thermal break. And the resulting R value at 1.79 is actually below compliance, below minimum compliance.
Yeah, no, that's that has a significant difference. Now, the other thing that we do know from our perspective is that if you go to the next slide, that if we're in an extremely high wind zone, we need to increase the number of fasteners from a standard 6 to about 9 per square meter to compensate for that wind uplift pressure that we may occur. And you run this calculation, which sort of, I guess, paints an even less glorious picture.
Yes, as you can see, even with the thermally broken fasteners, we're just about meeting the compliant R value for a roof system with 100 mil thick insulation, and using non-thermally broken screws or standard screw systems. Yeah, we're significantly below code compliance.
Yeah, no, that's and I guess at that sort of point there, you've actually got to start considering is your warm roof going to start generate moisture within that buildup? What's that moisture going to do to the structure? What's the moisture going to do to that, which is typically a steel fastener?
Yeah, so this is not even considered here, but you're correct. Obviously, with the thermal conductivity, you've got moisture problems in and around, and other problems around corrosion, movement, expansion, which I'm sure you were going to talk about.
Yeah. So this slide here that Jade's popped up is basically just a summary of Denise's calculations to make it a bit more visible. But in essence, basically the difference between using a thermally broken fastener and a standard screw fixing is you can actually get a reduction in the construction R value of up to 50%, which is incredible. I mean, the R value on the packet says 4.5, but when you install it, and it's actually far less. So, you can ask yourself, are you really getting what you pay for there? Awesome. All right. Hey, thanks for covering that, Denise. All those calculations will be out in the PowerPoint presentation. It'll be a lot easier to read. Right now, I'm going to talk about the third point, which is additional layers of redundancy or backup plans, or what we can actually install or build into our warm roof systems should things not go to plan. Much the same way as oxygen masks are put in planes, they're not used every day. But sometimes they're there in case things don't go particularly flash. So what I want to talk about is the particular, this layer here we put in the Nuralite warm roof system. So the first layer is a vented base sheet. You can see from this slide here, it consists of a diamond pattern, which is a self-adhesive patch, which adheres to the top surface of the PIR insulation layer. Now, what this does is it allows for any moisture that may be captured during construction, or any construction moisture, allows it to dissipate across the surface of the roof. What we don't want to do is have that moisture expand and create blisters and damage the membrane. So, excuse me, this is how we incorporate that additional feature in the Nuralite warm roof system. Now, this vented base sheet also is your backup plan should the roof be punctured. Now, we did have a situation many years ago where there was a warm roof that had been completed, it was installed, there was an adjacent metal roof that had not been installed. There was a bit of a wind event and a sheet of iron basically went tumbling across the warm roof and punctured the membrane. That's easy enough to find the hole and repair it, but during that weekend, of course, that all the rain had gone in and basically that void around the insulation had filled up with moisture. So with the inclusion of a vented base sheet, we're able to dry out and dissipate that moisture and get it out of the buildup. We don't want any moisture in there. We want to protect that insulation. We want to keep it as dry as possible. The same principle is actually carried on through our TPO layer as well, which has a fleece back facer, if you like, which is adhered to the surface of the PIR board. Again, this acts as a vapor diffusion layer and allows moisture to escape. Like I said, moisture could be from rain during construction or simply from Auckland's fantastic relative humidity we have during the summer. We have temperature changes and that can create moisture within inside that. So on the next slide, we've got a couple of images of what happens when we don't have a vapor diffusion layer. This particular roof is a single ply thermoplastic membrane. We've got moisture trapped during construction. This roof is not even in service yet. As you can, for those eagle-eyed installers out there, that gutter has not even been welded down to the sole yet. So it hasn't been finished, but we've got moisture entrapped within that insulation layer, which of course, once it warms up, it expands and creates blisters, which not only look unsightly, but they start to, I guess, degrade the membrane over time. And like I said, this is a brand new roof. It hasn't even been put into service yet. The next slide sort of depicts a similar scenario in a double layer torch-on system. What we're seeing here is, again, moisture trapped within the insulation layer underneath the membrane. It's a bit warmer, we can tell, because there's no snow on the roof. I think if there was snow on the roof, there probably wouldn't be any blisters because it would be cold. But as soon as that area warms up, obviously the moisture expands and creates those blisters. It's not a waterproofing leak. This roof's not leaking. However, I would have to question what the longevity of a membrane system that has these blisters inside it would be. I don't think you'd get a 35-year service life out of it at all. All right, we're going all right for time. Now, if you quickly go to the next slide, I'll run through this one. So when we were developing the metal skin warm roof system, this was one of the, I guess, prototype designs we looked at. Basically, what we did is we put metal skin on top of the insulation, and we had a giant fixing about 200 millimeters long, all the way from top to bottom. Now, when we got this WIFI model, what we did find is that there was moisture generation within the cavity of that top metal skin due to nighttime solar radiation, that the moisture inside that air condensated and formed and dropped on top of the insulation layer, which was a problem. Basically, that the internal climate for that profile was over 80% relative humidity for 90% of its life, which is not an ideal situation for steel. The other thing we saw when we modeled this was the mechanical fixing that ran all the way from the cold outside all the way through to the warm inside. Another thermal bridge, which we've already touched on. And the other problem that this created was that this top metal skin is actually going to expand and contract several times a day as the sun comes and goes and cools down. So there's a lot of movement on that particular fixing. So we moved away from that when we developed, if you go to the next slide, when we developed this particular system, Tricore, with our friends at Diamond. So what you'll see is different from the previous detail is we've actually got a ventilated cavity batten on the top side, which acts as our vapor diffusion layer, same as our membrane system. And in this particular instance, we're using a metal profile that has a plastic lug or a plastic clip. So we're not actually top fixing, piercing that metal skin. And we're allowing that metal skin to expand and contract as the sun comes and goes and does what it does. So that's the sort of the modifications we had to make to that to allow for that vapor diffusion layer. Right.
Hey, Shane, does that batten allow us to avoid putting a fixing all the way through to the steel purlin?
Yeah, it does. It does a couple of things like that. Yeah, like you said, the fixing actually sits in the structural batten and goes through to the purlin. which separates the fixing of the top metal sheet. The metal sheet is then able to do what it needs to do independently, and I guess at the end of the metal's lifespan, we can actually replace that metal top skin without having to disassemble the whole roof. So there's a couple of other advantages, I guess, separate the fixings in that particular system. So I'm just aware of time, and I've got a couple of minutes. I want to go to a couple of questions we've had, and then I'll recap on what we talked about. I'll ask the questions while I've got the panel in front of me here. This one might be for you, Denise. Can you explain the subtleties between the Glaser method and the woofie method that Peter mentioned earlier?
Sure. So the Glaser method is just a static or stationary calculation method where you've got set boundary conditions on either side of your construction system. For example, just one temperature and one level of humidity on the inside, and the same for the outside. And based on that, using your Backus tool, you're calculating a possible condensate of a period of 90 days. So that's how they do it in Europe. And that will be evaluated against a potential drying period of 90 days. So that is standardized for the climate in Germany, so that might not be applicable perfectly in New Zealand. And when we're looking at woofie, it does take dynamic boundary conditions into consideration. So we have actual climate data of the location that you're in for the external, which also considers radiation of sun and wind speed. And on the inside, we can then manage your internal conditions based on a little bit of that external climate and how much heating or cooling you put in on the inside. Plus, we can look at air leakage, water leakage from either side into any part of the construction. So it is a bit more sophisticated.
Wow. And that's something that you guys can do if someone needed to get some woofie modeling done. They can engage you guys to do that kind of stuff. Well, that's great. Okay. I've got another quick question here. Why isn't the metal tray classed as a vapor blocker, Pete?
Well, typically, Shane, that's because of the gaps between each metal tray's sheets. Some suppliers look to use a tape to bridge those gaps between the sheets. In our experience, this is not often enough to stop that moisture from getting into the build-up, and we prefer to have a dedicated layer to that vapor blocking, which is why we have our vapor barrier rather than just relying on the sheet and the tape.
Yeah, great. And just to follow on from that question on the same thing, how's that vapor barrier installed? What's its makeup?
So that is a self-adhesive bitumen layer with an aluminium foil to the top of it. So it's able to adhere to itself and to the substrate that it's put on, and then that foil helps to create that vapor blocking.
Okay, nice. We're getting questions in here thick and fast. That's great. Another quick one is the fixing of the PIR board. Does it have to go to do we have to hit the purlins, or can we go to the steel tray?
In our system, we typically just go through to the tray.
Yeah.
I don't know of any situations where we've gone to the purlin. Do you, Shane?
No. I know that in a high wind zone where we do need more fasteners than standard, we can increase the specification thickness of the liner tray, which will then give us additional holding from the screw fixings. And I guess we've talked about mechanical fixing, but there is another option available to us. We can actually adhere the full system, and we typically use that on a concrete substrate, or when we're using a tapered PIR system. What else have we got here? Do we have any other insulation materials we can use on a warm roof?
We do. We have rock wool, mineral wool insulation. We tend to use that in more of a hybrid build-up. So we'll prefer to use PIR over the majority of the section, and then where required, we can switch in the rock wool for things like going over intertenancy walls. Yeah, so that's the other option we have available.
Okay, excellent. I am aware of time. Now, I've got one question that came in early, and it's actually sort of been repeated many times, and it's more of a statement. It says, I'm familiar with warm roofs and the concept. They're great, they're wonderful, etc. But how do we actually connect to the warm wall detailing and other such details as windows, etc.? We haven't got time in this webinar to answer that, but it is a great topic, obviously very popular. It's been populated about 10 times already today. So stay tuned in the next couple of weeks. Our next webinar will be how we actually detail those tricky details, wall to roof, roof to window, floor slab, etc. So keep an eye out the next couple of weeks for that particular webinar. I've got a question here about stock supply and all that. That's also going to be a webinar we're going to cover in a couple of weeks, but at the moment we're all good for that. All right, we're not going to get through all these questions. So like I said, what we're going to do is we'll capture this Q&A document, we'll answer them as best as we can, and we'll fill them out and send them out to you all as a document. So hopefully today we were able to sort of enlighten you into 3 design considerations to think about when specifying a warm roof. Make sure your insulation layer is thick enough to eliminate condensation. Just because it says 4.5 R value on the packet, are you actually going to get a true construction R value on site of 4.5? Consider the effects of mechanical fixing through the continuous layer. As we sort of illustrated, the performance of the insulation can be affected by up to 50%. And then consider how we can add additional layers of protection. Now, we talked about a vapor diffusion layer. Someone in the Q&A in the chat actually mentioned, can we close off particular cells within the roof? That's also a good idea. So there are many ways to add additional layers of redundancy into your warm roof design. Thanks to my panelists, thanks to my producer. Thank you very much for attending. We had a lot of attendees today. Thanks for choosing such a wonderful charity, Denise. So they'll be very glad to receive their donation, no doubt.
Thanks for having me.
No problems. Yeah, look at the comments and Q&A. This could have gone on for ages. But I really appreciate everybody's participation today. We've just got a couple more polls we're going to run. I can't remember which order these come up, Jade. If you want to rate our presentation today, let us know how we can improve these for you. And the next poll is if you would like a direct follow-up from something that you're working on at the moment from someone in the panel. We can get in touch with you and assist you. We're all sitting at home pretty much with not a lot to do up here in Auckland. All you lucky level 2ers out there who are out skiing. I wish you all the best. All right, thanks very much, folks. We're going to leave it there. Thanks again to my panelists. Thanks for participating in the polls. All this information will come back out to you probably by tomorrow, and we look forward to seeing you again next time. So thanks very much for attending, and we'll see you on the next one. Thanks, team.
Thanks, everyone.